Okay, so we got to go over a guy named Kepler today. Okay, it's there's not going to be much in your notes about Kepler, but we're going to just go over Kepler here because some of his discoveries and some of the things he did were kind of important in helping us understand exactly how objects move within the solar system. Because way back when, like in the 1600s, okay, there was a lot of argument as to what orbited what. Okay, a lot of people, including credible scientists, thought that everything orbited the Earth. Okay, the Earth was the center of the universe. Okay, the terracentric or geocentric universe. Okay, and everything orbited the Earth, which of course we now know is ludicrous because the Earth doesn't have that much mass. Okay, but it was Kepler who actually proved that that was the case. Okay, now there's a bit of drama that goes into this whole discovery of his because this led to the biggest feud ever in science. Okay, between Kepler, okay, and Tycho Brahe. Tycho Brahe was very much the geocentric universe proponent. He believed everything orbited the Earth. He spent most of his adult life behind a telescope at night, not seeing the light of day, okay, studying the movement of stars and planets and things like that with his telescope. So he had acquired essentially a lifetime's worth of data on the movement of planets, okay, and the movement of bodies in the solar system. And unfortunately, what his data told him wasn't what he knew to be true, and that's that everything orbited the Earth. His data did not say that. So he said, maybe I'm just not good enough at math. Maybe I need to hire a mathematician to work my data to make it say what I want. Okay, because maybe I just don't understand it well enough. So he hired Tycho Brahe, or he hired Johannes Kepler, who was an out-of-work mathematician. So if you could get work, you took it, even if the job was tough. And the job was really tough because he was being asked to prove something that wasn't true, and every time he tried, he failed or succeeded, whichever way you look at it. Okay, he failed to prove Tycho Brahe right because Tycho Brahe was wrong. Okay, so here's what Tycho Brahe had observed. Tycho Brahe watched the other planets in the solar system. When he watched Mercury and Venus, they seemed to move predictably the way they should. Okay, they would pass the Earth and they would just go around the sun. Okay, but when he observed the outer planets, he didn't see that as much. Now, of course, he didn't live long enough to observe many of them making more than one orbit, but he was able to watch Mars pretty regularly. Okay, a year on Mars is about just under 2 Earth years. All right, so he was able to watch Mars's path through the sky for many years. He was able to see it complete many orbits. Here was his problem. Okay, he saw that Mars appeared to backtrack, that is, go backwards in its orbit every couple of months. Okay, so what would happen is he'd be watching Mars, and Mars would be moving predictably along in the sky according to a proper orbit, which he believed was around the Earth. And then, for some reason, at the same point in its orbit every time, Mars would do this, and then start to go back again. Now, obviously, a planet doesn't stop, turn around, go backwards, stop, and then turn around and go forwards again in its orbit. Okay, but that's what it appeared to do in the sky, so Tycho Brahe was understandably confused. All right, so he, again, gave his stuff to Kepler and said, make it work. And Kepler couldn't make it work because what Kepler discovered was Mars doesn't orbit the Earth. That's the only reason Mars would do this. Okay? The reason Mars does this is because Earth passes it. Because Earth orbits quicker. It's closer to the sun. So what happens is as Mars is orbiting and Earth catches up to it and passes it, it looks like Mars is moving backwards in the sky from Earth. Okay? It's like when somebody passes you on the highway. Okay, it looks like you're moving backwards if you watch them because they're moving past you. And so that's exactly what would happen with Tycho Brahe when he would watch Mars. Earth would pass Mars, and it would look like Mars was moving backwards, even though it was still moving forwards. It was just going slower. Okay, and that's what Kepler calculated to be true. But then, of course, he went to Tycho Brahe and said, yeah, you know all that life's work you gave me? It's wrong. Okay, at which point Tycho Brahe went, you're fired! And so began like this huge feud, okay? And it got worse because all Kepler did was keep all of Tycho Brahe's data and continue to prove him wrong in the scientific community for years and years afterwards. So essentially, he humiliated Tycho Brahe with his own data, okay, for years and years afterwards. You can understand why Tycho Brahe went to his grave hating Kepler's guts, okay? He also went to his grave still believing that everything orbited the Earth, even though we proved otherwise. Okay, so that's kind of what happened there. So what Kepler did is he took that data and he came up with what we now know as Kepler's laws of planetary motion. Okay, so what Kepler came up with is this. Okay, Kepler's first law is the law of elliptical orbits. Okay, he also found from Kepler's very meticulous, or from Tycho Brahe's very meticulous data, was that Earth actually changed speeds as it orbited the sun. There were parts of its orbit where it went fast and parts of its orbit where it went slow. Okay, not like radically different, but a little bit different. The only reason for that would be if part of this equation, which he didn't really know about, okay, changed. All right, he knew that centripetal force was this formula. We didn't have Newton's thing yet, but he knew that the objects were moving in a circle, and the things that could affect movement in a circle were radius and mass. Well, obviously the Earth didn't get heavier, okay, throughout its orbit, but if it got closer to the sun, that might explain why it was moving faster. And then at different points in its orbit was a little further away from the sun and moving a little slower. So he said, maybe the orbit isn't a perfect circle. Maybe it's actually an ellipse. Right? And so that seemed to fit with the data that Tycho Brahe had meticulously measured for him. Okay, so he came up with that idea. Okay, that's his first law. Kepler's first law is the law of elliptical orbits, which just says the law, or the orbit of any planet around another is elliptical. It's not a perfect circle. Okay, all right. Now, people are like, okay, fine, prove it. Okay, so he came up with his second law to help prove his first law. Okay, and the second law is what we call the law of equal areas. So this is highly exaggerated, obviously. The Earth's orbit does not look like this. Okay, but what he said is when the Earth is very, very far away, okay, or has a greater radius, it travels slower. So it only covers this much of its orbit, okay, during that time. But because it's farther away, the area of this sector is equal to the area of this sector where the Earth is moving faster, but is closer. Okay, so we just needed a mathematical proof, okay, for why the Earth could move faster here, slower there, and why we wouldn't really notice it. Okay, so this was this sort of mathematical proof. So the second law is the law of equal areas. Okay, a planet sweeps out areas that are equal in equal time intervals. All right, has anyone ever noticed that our seasons aren't all the same length? Right, some seasons are longer than others. That has to do with this. Okay. Some of the seasons are longer than others because the Earth's orbit is not a perfect circle. And as a result, some of the seasons have to be a little bit longer because we're moving a little bit slower during those parts. Okay. All right. So what that actually means, guys, is that spring and summer are actually when Earth is farther away from the sun. Okay. Yes, really. Okay. Because the seasons aren't caused by us getting closer and further from the sun. They're caused by what? They're caused by the Earth's tilt, okay? Because, I mean, there's not a huge difference, right? But the Earth's tilt makes a huge difference in the amount of sunlight we receive. So in case you've forgotten, okay, here's the sun, okay, and here's the Earth. There are only 2 days a year where the Earth is straight up and down. What 2 days are those? The equinoxes, right? Okay, the solstices are when we're angled the most, right? Okay, so on like March 21st and September 21st, the Earth is essentially straight up and down, and we get 12 hours of sun and 12 hours of night. Okay, but at other points in the orbit, okay, like on the solstice, for example, okay, on the winter solstice, we're angled like that. When it's our winter solstice, okay, in the southern hemisphere, it's the summer solstice on December 21st, okay, because they're pointed towards the sun and we're pointed away. And the Earth's not just a little slanted, it's 23.5 degrees, okay? It's significantly tilted. So when we tilt away, okay, we stay in the dark a lot more than we get into the sun. If you're in the Arctic, okay, that is in the Arctic Circle, then it's going to be always dark, okay? you'll get the what is it, 3 weeks or so where they don't see the sun, okay, because they're tilted away so far, okay. And then in the summertime, the opposite is true, right? On June 21st, we're pointed towards the sun, and we get like 17 hours of sunshine, which is awesome. It's the best day of the year, okay? June 21st, the longest day, okay? So that's what causes that. But the Earth's orbit is not perfectly circular, okay? So from Tycho Brahe's data, this is what Kepler came up with. He found the eccentricity of all the orbits of the known planets at that time, and then we discovered other ones afterwards, okay? We discovered that Mercury is 20%, okay? It's 20% away from being a perfect circle. So that's considerable, like it's fairly elliptical. And that's because it's very close to the sun, okay, and the sun influences it quite a bit, okay? Venus is almost a perfect circle, okay? It's less than 1% away from being a perfect circle. So it has nearly perfect, not an elliptical orbit, okay? Earth's orbit is about just under 2%, okay, off of being a perfect circle. Mars, okay, 9% away from being a perfect circle, okay. Ceres, which is the biggest asteroid in the asteroid belt, is 8%. Jupiter, about 5. Saturn, about 5. Uranus, about 5. So that seems to be a pretty common number, okay. Neptune, almost a perfect circle, okay, even though it's really, really far away. Pluto, on the other hand, is way off, okay? And this is one of the reasons why Pluto lost its status as a planet and became a dwarf planet, okay? Is because if you're looking at the way the solar system is set up, okay, here's the sun. All the planets except Pluto orbit in what we call the ecliptic, which means they can eclipse each other because they're all on this plane. They're not all in line, but they're all on this plane. Pluto orbits like this. Okay, not only is it elliptical, it's also out of the plane, which means it can't eclipse anything. Okay, but it does cross Neptune's orbit, right? So at some point they might crash into each other, maybe. Okay. Okay. So what we see here, guys, is if we're looking at Earth's elliptical orbit, okay, we can see that at this point where Earth is very far away, it moves at 105,635 kilometers per hour. Okay, here where it's moving fastest and it's closest to the sun, okay, it's moving at 109,289 kilometers per hour. So difference between its slowest point and fastest point, or furthest and closest, is 4,000 kilometers an hour. Okay, so I mean, when you're talking about an orbit that big, it's not that much. It seems like a lot when you just look at the numbers. Okay, now just so you know, there is a term for this point and this point. What's the term for the closest point in the orbit? Starts with P. I didn't expect anyone to know it. Perigee, and this is apogee. Okay, apogee is the furthest away, perigee is the closest. All right, so if you have an elliptical orbit, you have that. Okay, Kepler's third law. Okay, here's what Kepler discovered with Tycho Brahe's data. This was the ultimate humiliation of Tycho Brahe, okay, because it proved mathematically that everything orbits the sun. Okay, he found that if he took the period of a planet and squared it, then divided it by the radius of that planet's orbit, he would get a number, obviously. Okay, but what he found is if he did that for any planet in our solar system, it was the same number. If he took the period of Neptune, squared it, and then divided it by the radius of Neptune's orbit, cubed, he would get what he called the Kepler constant. Okay? If he did that same thing with Mars's numbers, he got exactly the same Kepler constant, right? Which proved they had to have a common central point to their orbit, that being the sun. Okay, so that was the mathematical proof, okay, that everything did orbit the sun, and we call this Kepler's law of periods, okay, because it uses the period and the orbital radius in order to calculate it. So essentially, what he could do was use this formula to predict where other planets in the solar system might be. Okay, so we had this formula as well as the gravitational wobbles in the outer planets' orbits that helped us to figure out where to look for Uranus and where to look for Neptune, because those two planets cannot be seen with the naked eye. Okay, they were discovered purely by telescope by using mathematics to predict where they should be based on how they would perturb the orbits of Saturn and Jupiter. Okay, so every time when Saturn would make its orbit, there were places in its orbit where it was pulled away from the sun. Okay, and the only reason that that Saturn would move away from the sun is if something large was passing behind it and pulling it away. Okay, so we were able to use that data to predict where Uranus would be, direct a telescope there, and discover it. Okay, same with Neptune. Pluto was more a stroke of luck because it was pretty small and isn't really going to move the orbit of Neptune very much, but okay, they were still able to discover it that way. Okay, making sense? Okay, so what you'll need to know are Kepler's 3 laws. Like, it would be super easy to make a multiple choice question that said, which of the following would Kepler not agree with? Since 3 out of the 4 would be his laws. So, copy down the highlighted stuff. Okay, number 1, the law of elliptical orbits. Number 2, the law of equal areas. Number 3, the law of periods. And then we're going to look at how you can use the law of periods to calculate and solve some problems. All right, so what Kepler's law of periods allows us to do is sometimes it allows us to shortcut a satellite motion problem. Okay, if we have the right information, we can solve a satellite motion problem a lot faster with Kepler. The drawback to Kepler is this. It only works if you have exactly the right information, whereas satellite motion going FC equals FG works all the time. Okay, Kepler's law only works if I know 2 bodies orbiting the same central point and I have just the right information about each of them. If I do, Kepler's the way to go because it's a lot faster. Okay, the other advantage of Kepler is I don't have to use seconds for period and I don't have to use meters for radius. I can use whatever units I want. We're only looking for a ratio. Okay, so I can use years instead of seconds and get much smaller numbers, okay, than I would if I was using satellite motion. So there's some advantages to Kepler, but its biggest disadvantage is you have to have just the right information. Okay, you always have the right information to go FC equals FG, so it's more reliable. Okay, whereas Kepler, if you have the right info, is nice and short. So we'll have a look at how Kepler's law of periods works here. Okay. Astronomical units, something that was on your quiz, but I changed it at the last minute because I forgot I hadn't talked about it yet. Okay, astronomical units. 1 astronomical unit is the distance from the center of the sun to the center of the earth. It's 1.5 times 10 to the 11 meters. Okay, so that's 1 astronomical unit. Okay, and we can use that in Kepler's law of periods in place of meters and have really nice small numbers to deal with when we're using it. Okay, so that's what 1 astronomical unit is. Okay, so for example, okay, Neptune we calculated was 4.5 times 10 to the 12 meters from the sun, but it's 30.1 AUs, which is a much smaller number. Okay, it's 30 times further away from the sun than Earth is. Okay, so we're going to do this calculation here. So I want everyone to write this one down, okay, and we're going to solve this one using Kepler's law of periods. Okay, so we know that Mars has an orbital radius of 1.52 astronomical units. Okay, that means it's 1.5 times further away from the sun than Earth is on average. Okay, we want to find out what its orbital period is. So what Kepler discovered was this. Okay, the period of any 2 bodies and the radius of any 2 bodies orbiting the same central point, when divided, comes up to the same number, Kepler's constant. So if I take the period of Earth squared and divide it by the radius of Earth's orbit cubed, it will give me the same number as if I did that with Mars's numbers. Okay, like we said, this was the death blow to Tycho Brahe's terracentric universe. Okay, this unequivocally showed that Mars and Earth have the same central orbiting point, and it's the sun. All right. So if I'm setting this up, okay, do I know the period of Earth's orbit? How long is it? 1 year, or 365.25 days. But I'm going to use years because I don't have to use seconds. I don't have to use days. Years is a nice round number. It's 1. Okay, it's 1 year. Okay, and how far is the Earth away from the sun? 1 astronomical unit. You see how you get nice small numbers to work with? And they're 1 lots of the time because you almost always use Earth as the second body when you do this. Okay, for Mars, we're looking for its orbital period, and we know its orbital radius is 1.52 astronomical units. So all I have to do is manipulate for the period of Mars here. So I'm going to multiply both sides by the radius of Mars's orbit cubed, and that will give me the period of Mars. All right, so what that'll look like is this. 1.52 cubed times 1 squared, because the period of Earth is 1 year, okay, divided by the radius of Earth's orbit, 1 cubed. Well, what's 1 squared? 1. What's 1 cubed? 1. This is sweet. Okay, so now all I have to do is go the square root of 1.52 cubed, and I have the period of Mars's orbit in years. All right. So it's a lot shorter, right? Like there's a lot less manipulating to do than there is with using FC equals FG. All right, so that means it takes Mars 1.87 years to orbit the sun. A stands for annum, which is year, okay, 1.87 years. All right, which means you'd only have a birthday one out of every 2 years, okay, because it's almost twice as far away, or takes almost twice as long to go around. Okay. Everyone kind of follow how that one works? Okay, so not overly difficult, and the nice thing again is that we can use nice small numbers when we're doing this calculation, unless the question specifies it wants the period in days or it wants it in seconds or something. Then you have to use seconds for the units or meters for the radius or whatever. All right. Okay, I want you guys to try question 1 and 2. All right, let's quickly have a look at number 1 here, because it's just like the one we did with Mars, except we're given Jupiter's numbers for this one instead. Okay, so we know that for Kepler, we have to have 2 objects that orbit the same point. Well, luckily, Jupiter orbits the sun, and so does the Earth, and we know the period of the Earth. Okay, and we know the radius of the Earth's orbit. Okay, and we know that that'll be equal to the period of Jupiter's orbit squared divided by the radius of Jupiter's orbit cubed. Okay, so if I want to get the period of Jupiter's orbit, I'm going to multiply both sides by the radius of Jupiter's orbit cubed, and then I'm going to square root that. Okay, so the period of Jupiter will be the square root of 5.203 cubed times 1 squared over 1 cubed. Okay, because those are Earth's numbers, one year and 1 astronomical unit. Right, and when we do that, we should get 11.87 Earth years, or about 12 years. Okay, so we'll have square root of 5.203 cubed. It's 11.87 years. Okay. All right, how many people have done number 2? Okay, I'll give you a few more minutes on number 2. All right, so this time it gives you the orbital period of Pluto in days. So you'll need to use Earth's orbital period in days. All right, so for number 2, okay, they've given us Pluto's orbital period in days, which now means I have to use Earth's orbital period in days, and that is 365 and a quarter. Don't forget the quarter. Okay, this is one of the corrections that they had to make in the textbook. That answer is not the answer you get if you use 365 and a quarter. Okay, if you use 365, that's the number you'll get. Okay, when they first printed the textbook, it was full of mistakes. I mean, literally full of them. They sent us a corrections booklet. I kid you not, it was that thick. Okay, it was like a quarter of the size of the textbook, and so we just said, you can have all of it back, because we're not handing out a corrections booklet and a textbook to every kid. So they ended up having to reprint all the books. Lesson here? Check your freaking work. I mean, before you send something to the publisher, you should check it over. There were a lot of mistakes in that book. Okay, so this is one of them. So we will set this up. We've got Pluto. Okay, so we'll have, again, period of Earth squared over the radius of Earth's orbit cubed is equal to the period of Pluto squared divided by the radius of Pluto's orbit cubed, and this time we're looking for the radius. Okay, so I'm going to bring radius up here and then move everything else over. So I'll have period of Pluto times the radius of Earth's orbit cubed. Okay, and that'll be divided by the period of Earth squared, and that will give me the radius of Pluto's orbit as long as I cube root it. Okay, so radius of Pluto's orbit will be the cube root of 90,553 squared times 365.25 squared divided, oh, sorry, nope, that's in the wrong place. That's supposed to be on the bottom. Okay, 1 cubed, okay, over 365.25 squared. Okay, so, whoop, not cube root of 53, yeah. Okay, and that's squared, okay, divided by 365.25 squared. Okay, so we're getting 39.464. Okay, they got 465. Well, I guess it rounds up to the same. Okay. Well, did I put the correct? Maybe I put the scanned corrected version on here. I know it was wrong before. Okay, so anyway, that's what we get. Okay, on that one. Everybody follow me there? Okay. I know that one was wrong when we first got the book. That was definitely okay. How many people have done number 3? Okay, work on number 3. See if we can finish that one before class is out. All right, so for number 3, it's again like number 1. It's like the Mars question we did before. We're looking for the orbital period of the piece of rocky debris. Okay, so we got period of Earth squared over the radius of Earth's orbit cubed equals the period of the rocky debris squared over the radius of the rocky debris's orbit cubed. Okay, and so we're looking for TR here, so we're going to multiply both sides by RR cubed. Okay, and when we plug in our numbers here, T will equal the square root of 45 AU cubed times 1 squared over 1 cubed. So when we take the square root of 45 cubed, we should get 302 Earth years, okay, on that one. So it's pretty far away. Okay? It would be kind of like the object that New Horizons is traveling towards and will fly by on New Year's Day. Okay, keep your eye out for that because it'll be cool, maybe. All right, that's it for today.